Hey guys, how's it going? Okay, so today we're going to talk about air resistance and friction. We have been discussing gravity
My
and
left
why
hand, I
things
have
fall.
a feather. In my right hand,
Got a video playing there. Okay, so we've been talking about gravity and asking ourselves, do objects with more mass fall faster than objects with less mass? We discussed gravity and gravitational force as well as gravitational acceleration. What's the difference between the two? And how they affect falling objects. So we already kind of talked about that. If you've not seen that video, go back to 2.7 and make sure you watch that. So we want to know, why do objects with different masses fall differently? So people used to believe that heavier objects or objects with more mass would fall faster than lighter objects, but that's not necessarily true. All objects fall according to the different forces that are acting on them. So some have um, air resistance involved, normal forces involved, applied forces, uh, forces of friction, whether it be dry or fluid friction, and that changes how things fall. Gravity isn't necessarily any different in terms of how fast it's pulling you down, but gravitational force can change depending upon the mass of the object. We already talked about that, how mass is a component of gravitational force. So, what is air resistance? It's going to be the first one we talk about. If you've ever had a little army man with a parachute, or dropped a piece of paper, or dropped a feather, or dropped a brick, you'll notice that all these different objects fall differently, and things that might change how they fall is if you have something with a surface area that may um, guide the object down more gently. So if I dropped a crumpled piece of paper and a not crumpled piece of paper, a regular piece of paper, the regular piece of paper is going to catch a lot of drag or air resistance, and it's going to slow the paper down. It's going to keep it from accelerating quickly at the floor. Whilst the crumpled piece of paper does not have the surface area to catch all of the drag, it's going to fall more regularly. It's not going to be as affected by the force of air resistance. So air resistance or drag, or we might even call it fluid friction, because it is a form of fluid friction, is a force in it that is in opposition to the motion of an object as it passes through air or another gaseous substance. So where you might see this, airplanes, right? We use the force of air resistance or drag to um, lift our plane. So they angle these wings at a certain point to where they will actually catch air resistance under the wings, and the more applied force moving forward will propel the wings upward. Some planes have moving wings that can actually change the tilt of the wing, and that'll allow for a greater force of drag, so it won't take as much thrust to shoot the plane up. But most planes have a very common tilt in their wings, which allows them to catch air and push them upward. So that's all it is. It's an opposing force, so it's going to go against the direction that the plane is traveling, and it's going to push the plane up by catching air underneath the wing. You guys might have heard of aerodynamics or things of that nature, and that's what we. This is one way we might use air resistance for us, just like a skydiver uses it in their parachute to keep them from accelerating at the ground at a rate in which they can't control their landing. So air resistance is something we use all the time. If you've ever been in sports and had to run with a parachute on to build your lungs, it can work against you too. It can be miserable, but at the same point, air resistance is kind of everywhere, and it really affects how things fall. And we'll look at that here shortly. So if you have seen the feather in the bowling ball experiment, you're probably asking yourself is why what's what what's going on inside a vacuum that changes the rate at which things fall? Well, normal air conditions or normal earth conditions, atmospheric conditions, we have air all around us, right? 70 something percent nitrogen, oxygen, argon. There's a bunch of components in air. And these gaseous substances can actually apply a fluid friction or air resistance against falling objects. And if the air resistance is stronger, or not stronger, but more proportional to the gravitational force of the falling object, it's going to decelerate that object a lot faster, and you'll see that with the feather. Now, with the bowling ball, the force of gravity is so large because the mass is so large that the air resistance doesn't have much effect on it. And also considering it's round, less of that force associated with drag is going to slow that object down. So gravity pulls all these things down at the same rate in terms of how fast we all accelerate at the Earth. We all accelerate at the Earth 9.81 meters per second squared. That's our gravitational acceleration. It's a constant, and that's not going to change. But gravitational force is dependent upon an object's mass. And whenever you have two forces competing to either unbalance or balance an object's motion, if they are closer in size, meaning air resistance is closer to gravity, then it's going to have a greater effect on the falling object. And that's what you're seeing in normal Earth conditions. Now, right here you can see inside a vacuum, this is to mimic space, right? In space we have no friction. That's why things don't lose energy. That's why these planets can keep orbiting for forever. And so what's happening here is these two objects are actually falling at the same rate because they both have a gravitational force. So they're both moving. However, they are moving at the same rate because their gravitational acceleration is the same. So as long as the force of gravity is the only force being applied on these two objects, they'll move at the same rate. When you have opposing forces, it will slow them down. So anytime the force of gravity is lower due to an object's mass, air resistance is going to have a greater effect on that object. And you'll see this in another example right here. So what's friction, right? Because I've been using it a couple times. Friction is a force resisting the relative motion of solid surfaces, fluid layers, and material elements sliding against each other. And friction is actually seen in all three examples there. You have surface friction, which is called dry friction. So anytime you have solids competing against solids. And then you have fluid friction, which is anytime you have air or liquid. And I know you normally think of fluids as liquid, but really fluids is anything that is not a universal, doesn't have a it can't change shape. So like if I put gas and liquid into a container, they're going to take the shape of that container. Whereas if I put a solid, it's not going to take the shape of the container. And that can change the way things apply forces on other objects that are moving. Because if you're moving in water or you're moving in air, the matter that they're composed of, the fluid, whether it's air or water, it's going to take shape around your body. Whereas a surface is just where a solid's just going to be in a confined area, and it depends on the shape of its matter. So, air resistance and liquids. Those are both examples of fluid friction. And then you have dry friction. So how do these compare to falling objects? Well, they're the same thing. They oppose motion. So if you are trying to push something across the ground, right, and you're trying to do it in, I don't know, a really soft surface like a linoleum or a polished concrete, right? They're going to slide a lot more easily than if you were trying to push them across sandpaper, okay? And well, that seems like a silly example to you. Think about this. Those different surfaces have different frictions. So friction is actually it's kind of a property of matter. So whenever you have friction moving against you, the stronger the friction, the harder it is going to be to push the object across the surface. It's an opposing force, just like air resistance. Air resistance is actually a form of friction. And if you had a plane that was flying in a really dense air versus something that was maybe a little bit lighter. Say I had two different types of gases, right? Some gases are significantly lighter than others. If I was flying in hydrogen versus flying in oxygen, the drag force associated with that is going to be a lot less in hydrogen because it's a lot less dense. So the air friction is going to be significantly less, right? If I was trying to swim in a giant puddle of, or not puddle, I should say, pool, giant pool of honey, it's going to be significantly more difficult than if I'm trying to swim in water, right? And that's because there's significantly more friction applied by the honey. So these are all examples of friction. It's an opposing force, and it's going to change the way objects move. So what this comes down to is that all objects will move according to the sum of forces. And they may also not move according to their sum of forces. And I'm going to leave you at that, but I'm going to explain the later of that. So if I have two sets of people, right, two pairs of people, and they're both pulling on a tug of rope, and you have the group on the right pulling with 500 newtons of applied force and the group on the left pulling with 500 newtons of applied force, how is either group or that flag in the middle going to move? They're not, right? Because they're equal. You're applying the same amount of force. They're going to be at a stalemate. And this is similar to unbalanced forces, meaning if I had 500 on the right, 300 on the left, 500 is going to overcome the 300. And if you think of all forces acting on all objects just like that, things will move according to the forces that are being applied on them. And we're going to get into that whenever we talk about force diagrams, Newton's laws, and the sum of forces and net motion. All right, that's all I got for you guys today. We'll talk next time. All right, bye.